Welcome to this video on Desiccant Dehumidifiers. In this session, we'll explore the core principles that make these systems work, examine how moisture is captured and released, and look at the components that enable continuous and efficient dehumidification. The content of this video is structured around three core concepts. First, we'll examine the principle of operation, how desiccants remove moisture from air. Then we'll explore the regeneration process, the thermal mechanisms that restore the desiccant's moisture holding capacity. Finally, we'll break down the main system components and materials used in real-world HVAC applications. The learning objectives of this video are, well, by the end of this video, you should be able to explain how desiccants remove moisture from air and how they are thermally regenerated for reuse. Let's begin with the question. Have you ever been in a building that felt uncomfortably humid, even if the air temperature was fine? This is a common problem in conventional HVAC systems that struggle with latent loads. Desiccant dehumidifiers offer a different approach, and potentially a more effective one. Let's start for the principle of operation. Desiccant dehumidifiers function differently from conventional cooling-based dehumidifiers. Instead of lowering the temperature below the dew point, they remove moisture directly, using special materials. When humid air passes over the desiccant surface, water vapor diffuses into the material. This diffusion happens at the microscopic level, within the pores of the desiccant. This moisture removal is known as adsorption, a process in which water molecules bond to the desiccant surface through chemical attraction forces. It's a powerful way to dry air without causing condensation. The figure here shows a rotary desiccant wheel with two separate air streams. The process air enters on the upper right here, and the upper left, at state 1. Here is warm and it's humid. As it passes through the rotating wheel, it becomes dry and warm, and exit at state 2. Simultaneously, the regeneration air enters on the lower right at state 3. It's hot and moderately humid, and exits at say 4 when at a lower temperature and high humidity. And it can be saturated here. As the desiccant absorbs moisture, it also releases heat, known as heat absorption. This is similar in magnitude to the heat released during condensation, and it explains why the process air heats up as it dehumidifies. So the wheel ends into a higher temperature than the air, and it transmits heat towards the air. The regeneration air absorbs this released moisture, effectively drying the desiccant. This dual stream configuration, combined with continuous rotation, enables uninterrupted operation of the system. A typical desiccant dehumidification system is composed of a rotating wheel or fixed bed that holds the desiccant, as well as a regeneration air heater filters and circulation fans. Solid desiccants are designed with extremely porous structures at the microscopic levels. This high internal surface area allows them to efficiently capture moisture from the air as it passes through the system. This microscopic porosity is what makes materials like silica gel so effective in HVAC applications. Common desiccants include solids like silica gel and activated alumina, as well as liquids like lithium chloride and triethylene glycol. For HVAC systems, solid desiccants are preferred due to their durability and ease of handling. So let's recap. Desiccant systems remove moisture but add sorption, a mechanism very different from refrigeration-based dehumidification. Regeneration restores the desiccant using thermal energy, allowing for continuous cycling between wet and dry states. These systems are built from simple but powerful components: porous desiccants, fans, heaters, and rotating or fixed media beds. So I invite you to continue learning. You can explore the psychrometric behavior of desiccant dehumidification and how air properties shift during the process. Review key concepts like enthalpy conservation and how to interpret psychrometric charts to track changes in air temperature and humidity. Finally, you can reflect on which types of buildings and climatic conditions benefit the most from desiccant dehumidification. Thank you for watching this video.